the reason why all these things happen. And what you started investigating yesterday was the first of the gas laws. The difference between a law and a theory is not about certainty, it's about what question you're trying to answer. Theory tells you why they are. Gas laws describe how the gases behave, what they do. So, to do the lab you guys are doing, do you even have to know that there's molecules? Did Boyle know that there were molecules? No, when he discovered this relationship, he didn't know there's molecules, so he could not have been using the kinetic theory. He had no idea why it worked, but he saw the mathematical relationship. And that's pretty often. Once you know the theory, it's pretty easy to predict. The law has to agree with it. But you can come up with the law without knowing why. Because if you do the same thing, and it always changes in the same way, then you can count on it changing the same way the next time, even though you don't know why. And gas laws, our gas laws are best written as a mathematical equation. So what do we have to include in our equation? What can we change about a gas? What variables do I have to worry about in my equation? Okay. Well, it turns out to describe a gas, there's 4 things. There's 4 variables that go into completely describing what a gas is like. Some of the variables are familiar. Pressure. When you change the pressure, you change the volume, right? So you can change that. The things you change about the gas. Temperature. I mean, on the bell work today, you talked about how temperature should affect collisions, right? So you could predict how it should affect volume. What it's going to do to the size of that container. Volume's the third one. And the fourth one is one we usually forget about because we deal with sealed containers. Most times we make sure this container's sealed. The reason why we seal the container, so we don't change how many particles there are. But we're not going to count individual particles. We're going to count moles. So there are 4 variables. Anybody want to solve equations with 4 variables? If I want to solve for 4 variables, I got to have 4 equations. Ugh, it's ugly. Actually, what scientists really want to do is they want to see just 2 of them. How if I change one affects the other. So if you think about what you did yesterday, you're investigating pressure and volume. So what'd you do? You made sure the syringe stayed on. So you always had the same number of molecules. And we didn't heat or cool the gas. So it was always at the same temperature. So I didn't change the temperature, and I didn't change the moles, so I can see how pressure and volume are related to each other at constant temperature. Okay? What they do is they keep 2 of them constant and see what happens to the third one. Let's see what happens to the other 2. Okay? So you were keeping pressure and volume. We wanted to investigate pressure and volume, so you kept the other 2 constant. You sealed the container, and you didn't heat or cool it. Okay? For most of this chapter, we're going to assume that gases behave ideally. And we've already talked about this. I just haven't put the word ideal gas with it. Ideally. Ideally means perfectly. As in the ideal, the perfect. Okay? Okay? So let us know, it doesn't really exist. No gas is perfectly ideal. But it makes the math easier. We will learn what you do when it's a real gas, what do real gases behave like, instead of these perfect things in our head. We'll see what the math looks like. It's not that the math is hard, it's tedious, it's just a lot longer. Okay? And you don't need to do it most often because it works pretty well. That you're getting tiny errors that you probably wouldn't even notice. And what do we mean by behave ideally? We've already talked about it. We assume the particles have no size. Because the math behind this says that the particles can be anywhere in the container. But technically, they can't be where there's another particle. So we're just going to pretend the particles don't have any size, so I don't have to worry about that. We know it's not true, but it's usually okay, because it's like 1/1000th. So that's what we're ignoring. So it doesn't usually make that big a difference. Okay. Second one is we're going to assume that molecules don't attract each other. But we know molecules attract each other. How do we know molecules attract each other? Because they're solids and liquids. That's how we know, because if they didn't attract each other, we wouldn't have solids and liquids. So we pretend like they don't attract each other when they're gases, but we know they really do. Okay? So again, no gas for which this is true. When does it work? It works if the temperature is high and the pressure is low. So the higher the temperature, the better we trust our numbers. The lower the pressure, the better we trust our numbers. What do we mean by a high temperature? A long ways away from the boiling point. Way above the temperature it would boil at. Because if you're near the point where it boils, they'd be sticking to each other. Which is the opposite of what we want. Right? And low pressure means about 1 atmosphere or lower. You guys are investigating Boyle's law. We're going to talk about Charles' law today. Charles. It's his last name. Okay. And Charles' law is about the relationship between volume and temperature. So let's think about that Bellwether question, the last one. What should happen to the volume when you raise the temperature? Well, the molecules are going to move faster, right? So they're going to hit that side of the container more, which is going to make that container get bigger, right? Okay. That means they're directly related. If I raise the temperature, I raise the volume. So volume of a gas is directly proportional to the Kelvin temperature. But notice this. If the pressure is held constant. The real thought here is, if I've got a pressure on the outside of my container and I heat the gas up on the inside, they're going to hit more often, and then it will get so the inside will win for a while and the container will get bigger because there's more pressure inside than outside. And it will keep expanding until the pressure inside equals the pressure outside. The pressure inside will decrease as it expands because as the volume goes up, the pressure goes down. Right? So you start off with a higher pressure because you got the things moving faster. It's got to equal the outside one, so it expands until the pressure drops far enough. It pushes until the air pushes just as hard. Or another way of looking at it, as it expands, the molecules have to travel further before they hit the wall. And the wall's got a bigger surface area. Right? So as the container gets bigger, that pressure's got to drop. Wow. See how it's actually tied into what the Boyle's law. Because Boyle's law, we kept the temperature constant, Now we're keeping pressure constant. So they talked about those Ks. Okay? Here is what a direct relationship looks like. V equals K times T, where K is some constant. And that K is only constant for that pressure and for that number of molecules. So nobody ever bothers to figure out K unless they're trying to make a point like I am in the lab. Right? Say, well, why do we talk about it? Well, if we were to solve for K, we'd solve for K by dividing both sides by T. Reasonable? And the reason why we want to be able to write that is because if I can write that, I can write this. The first volume over the first temperature equals the second volume over the second temperature. V1 over T1 equals V2 over T2. And the reason why that's true is V1 over T1 has to equal K. V2 over T2 has to equal K. K has to equal K. Make sense? So as long as I don't change the pressure or how much gas, I got a sealed container and I don't change the pressure, volume 1 over T1 equals V2 over T2. Okay? And what would the graph of that look like? What would the graph of this look like? If I put y equals mx plus b. This is a line, right? This is the equation of a line where that crosses the axis at the origin, where your y-intercepts the origin. That make sense? So that's what the graph's going to look like. I mean, think about it. Twice the temperature, twice the pressure, 3 times the temperature, 3 times the pressure, or 3 times the volume. Right? I'm going to get a line when I graph that. Okay. Strange thing is, I said every different volume of gas has a different K. Okay. Every different pressure has a different K. But strangely, if you do a bunch of them, there's a pattern. Okay, say the first one looks like that. The next one will look like this. The next one will look like this. Okay. They have different slopes, but they all have the same x-intercept. Now, what is that x-intercept? That x-intercept is the temperature where the volume would be 0. They all have the same temperature where they'd have 0 volume. And surprise, surprise, that temperature works out to be right about negative 273 degrees Celsius. That was the first definition of absolute zero. They didn't know there were molecules yet, but they knew that there was a lowest temperature. It would be the temperature at which you would have 0 volume. And all gases had the same one. So they used to the reason why I put dotted lines is because it's not going to be a gas here. So you have to extend the line. So if you extend those lines where it's not a gas, someplace along the way it's going to turn into a liquid. But if you extend the line, they all cross the axis at the same point. Our first definition of absolute zero. Okay? So, what is the temperature of a gas that expanded from 2.5 liters at 25 degrees Celsius to 4.1 liters at constant pressure? Hey, that looks like number 1 on the blue piece of paper. We don't have to take the time to copy that down because it's number 1 on the blue piece of paper. Okay? Still work them out though. Okay. So they want to know a temperature. What is the temperature? They give me a volume and they give me a temperature. So I have to decide whether to call 25 degrees Celsius temperature 1 or temperature 2. It does not matter which one I do. But if I choose this to be temperature 1, then the 2.5 liters is volume 1. If I chose that to be temperature 2, then the 2.5 liters would be volume 2. It's what the set of numbers belong together. Okay? And the 4.1 liters is volume 2. And we must be looking for temperature 2. So do I have an equation that has those pieces in it? V1, T1, V2, and T2, right? So I got V1 over T1 equals V2 over T2. And I want to solve this for T2. Okay. This will be the most frequently missed question. A question like this will be the most frequently missed one on the test. Because somebody will give me a decimal point for an answer. Because they will forget the first rule of algebra is you can't solve for something on the bottom. So my first thing I have to do is multiply both sides by T2. I got to get T2 off the bottom. Actually, I got to do something to get T2 off the bottom. So I can multiply by both sides by T2. I can cross multiply. Right? That would get T2 off the bottom. Or I could just flip both sides. Because that should work too, right? So I got to do something to get T2 off the bottom. I usually do the cross multiplying. V1 T2 equals V2 T1. And I want to solve it for T2, so I got to divide both sides by V1. So that's my equation. V2 T1 over V1. So V2 was 4.1 liters. T1, now I know you want to write 25 degrees Celsius, but if you do, you'll get it wrong. Okay? Because what's half the temperature of 25 degrees Celsius? I know you want to say 12.5, but it's not really. Really, negative 140. Why? Because I don't work in Celsius. I've got to work in Kelvin. It's got to be times 298K. Does not work in Celsius. And V1 was 2.5 liters. So 4.1 times 298 divided by 2.5. Notice I kept all my units so I can make sure they cancel out and give me units that are the kind I want. Do that, I get 490, because I had 488 and there's only 2 sig figs in my 4.1 and my 2.5. And that is Kelvin. The last thing to check is if you make a mistake, it's going to be to get something upside down, and it will change the wrong way. My volume went up, so my temperature should go, well, they're direct, so the same thing should happen, should go up. So I got a bigger temperature. Okay, if you tried this with 25 degrees Celsius, you'd see that you got a different answer. If you put 25 degrees Celsius in there, you get 41. 41 liters. Or 41K. 41 degrees Celsius, sorry, degrees Celsius. And that would look good. Oh, the temperature went up because I went from 25 to 41. But what if I had cut the temperature in half? See how it would be different in Kelvin versus Celsius? What would you do if it was a negative Celsius? Yeah, that's not going to work. So Example number 2 is the easy one, the easy version. Now, it may seem like silly for me to go through the process of figuring out which equation to use, but we're going to end up with 9 of them. We're going to end up with 9 equations. So figuring out which one to use is the important part. Okay, I got 8.3 liters. That's a volume. 17 degrees Celsius. That's a temperature. You don't have to copy down. It's number 2 on the blue sheet. Heated at 96 degrees Celsius. That's a second temperature. So that means 17 must have been the first temperature. And the 8.3 must have been the first volume because it went with the 17. And they want to find the final volume. They want V2. Anybody know an equation that has those 4 pieces in it? Why, Charles law. V1 over T1 is V2 over T2. Now I'm trying to solve for V2. It's already up top, so I just have to get it by itself. Right? So I'm going to multiply both sides by T2. And that gets me my equation. V2 equals T2, V1, T1. T2 is 96 plus 273 is 369? No, 370. No, 369 was right the first time. Okay. Times V1, 8.3 liters. And T1 was 17 degrees Celsius, which is 290 with a decimal point K. To remind myself that was 3 sig figs. 369 times 8.3. Divided by 290 is 11. I get 10.56, but there's only 2 sig figs, and my units are liters, which is good because I was looking for a volume. Think about if I put the numbers for Celsius in there, it would have been over 5 times as big versus not even double. See how Celsius and Kelvin will give you different answers. You got to work in Kelvin. Really complicated math? That's what that stuff has you do tonight. Okay, so now let's talk about how you are going to finish up the lab. So when you left yesterday, you had Logger Pro running, right? And you could not save. By the way, you couldn't save that Logger Pro file. It won't let you save things on that laptop. Okay, it wipes the laptop every time. You don't get to save. Okay, so when you first open up Logger Pro, it looks blank. So what you can do is, I got somebody else's report, and see you got your report, you got your data from the last time, right? So you made this table. It's on your Google Doc, so I opened up somebody's Google Doc, and I push Control-C to copy that data. And then I can go over here, and in the blank one, not opening up the Logger Pro, push Control-V, and it pastes it. And then I can go back, grab the next column, Control-C, Control-V, and for some reason you got to delete this first set. Data, actually, where's it? Oh, push delete, it goes away. Okay, it's hard to see because they're really light, but all the points are there. Okay, and if you remember, you guys did analyze, linear fit. Nope, I'm sorry, undo that. Don't want that. We did analyze, linear fit, curve fit, right? and you picked ax to the n. So if I remember right, this is about where everybody ended, right? So you've got the same graph. It's easy to recreate that same graph. Make sense? So work on that for the last 25 minutes, because you should be able to finish up those last pieces. Okay? And if you get that done, then Mr. Green is overly prepared. And 3, 2, 1. If you get that done, there's this. See, I really couldn't give you the whole period on this. You don't have a whole period's worth of stuff to do.